sky never lied and brought me to the dark. One by one into the fire.
Mankind has a new eye in space. The James Webb Space Telescope will be the perfect machine for astronomy for many years to come. The instrument will allow researchers to look deeper and more precisely into space than ever before. They want to explore the early history of our universe and follow the trail of the first galaxies and stars. The images provided by the super telescope will open up a whole new dimension in observing the universe and be a source of amazement to astronomers.
Astronomers have been looking up at the night sky and studying the stars for thousands of years. However, they encounter a few problems, as they can only do so at night. There's also the Earth's atmosphere that distorts the light and causes the stars to twinkle. And thirdly, scattered light from cities also interferes with our view. This changed abruptly with space telescopes. From up there, we can now observe stars around the clock, without any scattered light, and very importantly, without distortion from the atmosphere, which is why we can see the entire diverse spectrum of starlight today. From infrared to visible light, right down to UV light and X-ray light.
Kourou Spaceport in French Guiana, December 2021. After more than 20 years of construction, an Ariane 5 rocket is about to launch the James Webb Space Telescope into space.
When you get a satellite, like the James Webb Space Telescope, and you know what's behind it and how much responsibility you have, especially towards a partner like NASA, it has to go well. There's no room for mistakes. And I can tell you that people are pretty tense and sweating profusely when standing at the launch pad, while the countdown is running all the way to 0, and it's all systems go.
6, 5, 4, 3, 2, unité, top!
In a picture-perfect launch, the Ariane 5 carries the James Webb Space Telescope into space on December 25, 2021. The launch into orbit is so precise that the telescope uses no fuel for corrections. This boosts the mission time from 10 to at least 20 years. The engineers are proud.
A satellite of this size and importance, which NASA has built under its leadership, is of course a jewel. And naturally, you want to transport this jewel safely to where it is needed.
The telescope, built in the USA, was transported by ship to its launch site in South America. There, after final tests, it was placed inside the nose cone of the rocket. James Webb, the most expensive and most powerful instrument in astronomy to date, is a joint project of NASA, the European ESA, and the Canadian Space Agency CSA, with the Americans in a leading role.
The fact that NASA and ESA have entrusted us to launch this telescope on an Ariane 5 rocket is an indication of the huge confidence that NASA has placed in us.
The exploration of the early stages of our universe is one of the main missions of the James Webb Space Telescope. The observation of stars and planets within our galaxy will also play an important role. And looking inside the atmospheres of extrasolar planets. The scientists are delighted with their new instrument.
We received a fantastic image of a star-forming region. It was kind of a birthday photo after a year of science by James Webb. You can sit in front of it for hours. You can look at parts of it in greater detail. But we don't just get photos, we also get spectra. And these are often more interesting to scientists than the photos themselves.
The researchers had to wait a long time for their new instrument. Development of the telescope began back in 1996. Construction started in 2004. The costs skyrocketed, and the project was nearly abandoned. In the end, it cost a good $10 billion, far more than estimated, which is why the James Webb Telescope was dubbed by some of its critics as the telescope that ate astronomy.
We saw that the project was delayed mainly because the technical difficulties were underestimated. And of course, there were times when we asked ourselves, is the project even feasible? And can it be financed? But in the end, we prevailed, and it became a big success.
The technology of the new telescope is unique. It is a masterpiece of engineering. And the James Webb Telescope is huge. To fit on board the European space freighter Ariane 5, the telescope with its giant mirror had to be folded up into a piece of high-tech origami that could only be unfolded again out there in space. The individual assemblies of the telescope are brought into position piece by piece, a complex process that takes 2 weeks. First, the big multi-layered sun shield is mounted. This is followed by the secondary mirror, and then the huge primary mirror. The instruments are then slowly cooled down to operating temperature. After its launch, the most delicate phase in the commissioning of the telescope was its deployment in space. In the end, the largest observatory ever stationed in outer space flies through the void.
There are more than 50 elements where there would only have to be a single failure and the telescope would not have worked. And I always imagined that I would never get on an airplane if the pilot said, I have 50 elements here that, if one of them fails, will crash.
The new super telescope represents a revolution in astronomy. After the success of the Hubble Space Telescope, James Webb is the next big step towards exploring the universe. Right from the start, it delivers breathtaking and fascinating images. With the James Webb Space Telescope, the researchers embark on a journey through time that takes them more than 13 billion years into the past.
We are able to carry out measurements of events that took place 300 million years after the Big Bang. 300 million years compared to 14 billion years for the entire universe, which is really sensational, because it means we can go back to the early days of the universe shortly after the Big Bang. And we can also see how the universe expanded and individual galaxies formed and continue to form.
Never before has humanity been able to peer into the depths of space with such precision. The researchers want to use the James Webb Telescope to find the very first stars and galaxies, to see the universe as it looked more than 13 billion years ago. With their new instrument, researchers are hunting for the first light, the light of the primordial galaxies, which illuminated the previously pitch-black universe just 300 million years after the Big Bang.
What can the James Webb Telescope actually do better than the Hubble telescope? There are two things. First, it can capture 6 times more light and can therefore see much dimmer stars and galaxies. And it can do so with even better detail. And second, it can see further into the infrared and therefore further into the past of our universe, right back to the beginnings of stars and galaxies. Does this make the Hubble telescope superfluous? No. You could look at it this way. The two will share the tasks. Hubble will look at the closer stars, and James Webb will look at the more distant stars. What does the end of the Hubble telescope look like? Well, if all goes well, it will remain operational until around the early 2030s. During this time, it will get closer and closer to the Earth due to the residual air resistance until it burns up in the atmosphere around the end of the 2030s.
The Hubble Space Telescope once opened up a completely new perspective on the universe. Hubble works in visible light, but also in the ultraviolet and near-infrared range. The images are usually superimposed and colored for clarity. The results are views of our universe that continue to amaze us even today. It was these images that brought the cosmos a little closer to the layman.
The Hubble telescope has completely revolutionized our conception of the universe. Not only do we now know the age of the universe, but we also know its size. We've discovered planets. We have actually found new things with the Hubble telescope everywhere we've looked. In other words, I think it was the Hubble telescope that truly made us realize the immense vastness of the universe for the first time.
More than 30 years after its launch, the Hubble Space Telescope is still in use. Hubble also ushered in a new era of observation that astronomers had previously only dared to dream of. With Hubble, researchers were now able to explore regions of space that were previously completely inaccessible to them. For a long time, the telescope orbiting the Earth was the most powerful instrument in astronomy. Hubble has made discoveries that researchers could not have predicted. And it continues to deliver images of bizarre and breathtaking beauty to this day. Sculptures of gas and dust formed by dead stars. Wonderful images of so-called planetary nebulae. It was the Hubble Space Telescope that for the first time allowed a precise look into the highly dynamic center of our Milky Way. It pinpointed and visualized the birthplaces of new stars, and it provided the near proof that there is probably a huge, massive black hole at the center of every galaxy. Using the Hubble Space Telescope, astronomers have determined the age of our universe and studied the atmospheres of extrasolar planets for the first time. Hubble has completely revised our knowledge of the universe and, at the same time, opened up new fields of research.
The interesting thing is that telescopes are always built for certain purposes. You seek to achieve certain scientific aims, and that's how you define the technology available in these telescopes. But then you uncover a lot of things that are completely different, that you didn't expect at all. And I think that's also what you can now expect with James Webb, that we'll find many surprising things.
One major difference between the Hubble and James Webb Space Telescopes is their location in space. The Hubble telescope orbits the Earth at an altitude of around 540 kilometers. This allows for repairs and service missions. The James Webb Telescope, on the other hand, is located at a distance of 1.5 million kilometers from the Earth. It orbits around the Sun at the so-called Lagrange point 2, also known as libration point 2, a place of equilibrium in celestial mechanics, a kind of parking lot in the solar system.
The L2 point is very special, and this is exploited. Why? At this position, the James Webb Telescope has the Earth, Moon, and the Sun at its back. Because of its large heat shield, it's constantly in the shade, which means it can be kept at minus 225 degrees Celsius, which is enormously important. However, it also has a disadvantage, because when we're at this point, the Earth shades the Sun's rays, meaning there would be no electricity on the James Webb Telescope. And of course, that wouldn't work, and that's why we move in a small circular orbit around this L2 point, and in such a way that you can constantly see the Sun's rays. This has the added advantage that you can also communicate better with Earth.
James Webb can look much farther into the past of the cosmos than Hubble. Even the first images that the new telescope delivered left researchers amazed and hoping for new discoveries. The oldest galaxies found by the Hubble telescope so far date from around 500 million years after the Big Bang. Researchers were counting on their new instrument, enabling them to find a whole host of galaxies from the time before Hubble's reach. And James Webb is fulfilling their hopes. The telescope can detect the dim light of galaxies at extreme distances that formed only 300 to 500 million years after the Big Bang. With this new instrument, we are learning more about the distant galaxies, and therefore also about the formation, structure, and development of our universe.
On the one hand, we want to know how galaxies are formed. We live in a spiral galaxy. We see a lot of galaxies when we look into the early universe. But we also know that at the very beginning, the universe was completely homogeneous. In other words, how does a galaxy emerge from this homogeneous structure? That is the first question. And that means, of course, that we want to study galaxies as young as possible in the early phase of the universe. And these galaxies are very dim in their light. This means that we need a telescope that is particularly powerful. The next thing we want to understand is how do all the elements actually get into our bodies? Hydrogen and helium were created in the Big Bang. All the other elements were formed in the stars. We want to know how these stars are formed and how they develop and later release these elements back into the universe.
Despite its service of over 30 years and the stationing of James Webb in space, Hubble continues to deliver important findings. It generates 150 gigabytes of data for science every day. In the end, it is also about the discovery of extraterrestrial life in space. Now, with the James Webb Space Telescope, researchers hope to come a big step closer to this goal.
Ich habe eine Unze Gold gewettet. Ich weiß gar nicht, was eine Unze.
I wagered an ounce of gold. I don't even know what an ounce of gold is. I bet an ounce of gold that life would be discovered in the universe sooner than a human being would set foot on Mars.
Einen Fuß auf den Mars setzen wird.
With spectroscopy on planetary atmospheres, we will at some point find an atmosphere that we can only explain through biological activity. I'm convinced of that. I'm 58 now, so I hope they're quick about it. I would like to live to see that.
The successful commissioning of the James Webb Space Telescope has also opened up new avenues for researchers. They now have two eyes in space, each providing a different view of the universe. Researchers are combining the data from the two telescopes and gaining unusually detailed insights into our universe. Together, covering a much larger range of the electromagnetic spectrum, the two instruments complement each other. In this way, astronomers hope to gain an even better understanding of the properties of cosmic objects. Hubble's keen eye in visible and ultraviolet light is enhanced by the data from the infrared range provided by the James Webb Space Telescope.
What's special about the James Webb Telescope? Two things. First of all, it can see much further into infrared. Why is infrared so interesting? Well, when the galaxies and their planets were formed, they did not yet emit any visible light because they were not yet undergoing hydrogen fusion. What happened was that the primordial cloud collapsed, becoming hotter and hotter by a few hundred degrees Celsius, and emitting thermal radiation in the process, just like a hot stovetop. And this is exactly what the James Webb Telescope can see. What's more, the James Webb is much more sensitive. This means that it can still see the very weak radiation of the first galaxies at the beginning of our universe. So only this combination of sensitivity and infrared capability allows us to see the first galaxies at the beginning of our universe.
Their new instrument provides scientists with images of previously unimagined quality, such as this James Webb image of the dwarf galaxy NGC 6822, also known as Barnard's Galaxy, showing millions of stars in incredible detail. Webb's infrared eyes also reveal the turbulent phase of star formation. As a baby star grows, it ejects very fast gas jets from its poles. These are short-lived structures that are formed when the jets collide with interstellar matter, and which astronomers refer to as Herbig-Haro objects. The primary mirror of the telescope has a diameter of 6.5 meters. The mirror segments are coated with a layer of gold and an additional layer of silicon for protection. Nevertheless, there has already been minor damage caused by a rare, larger micrometeoroid.
This has no influence on the quality of the measurements. They are carried out perfectly. But it is a minor flaw, if you want to call it that. It's like a new car. You're upset that your pride and joy got its first little scratch. However, it is still fully functional and efficient.
The construction of the primary mirror, which weighs around 700 kilograms, and especially the polishing of its individual segments, was considered the most difficult technical challenge in the construction of the James Webb Space Telescope. One of the biggest hurdles in the planning was the weight. That is why the elements were made of beryllium. This rare metal is light, but extremely rigid. The individual elements are given a perfectly fitted protective cover for transportation and installation. The finished mirror has a surface area of around 25 square meters. The telescope's secondary mirror is mounted on a support structure in front of the primary mirror. The entire unfolding sequence of the mirror system was extensively tested on the ground. In addition to the weight advantage, the beryllium used for the mirror elements hardly changes shape at all when the temperature fluctuates in the freezing cold of space. After 2 weeks of flight, the mirror had cooled down sufficiently for the first alignment tests.
Beryllium is a very rare metal. It's only mined in a few places on Earth. But beryllium is a very special metal. It's lighter than aluminium. This is very important because James Webb's mirror is much larger than Hubble's. But the weight is less than Hubble's mirror because beryllium is used. It's much harder than any other metal. It doesn't warp, especially at low temperatures. And that's why beryllium is such a great material for the James Webb.
The second striking feature of the telescope is the huge heat shield, a solar sail made of 5 ultra-thin layers of the special plastic Captain. Thinner than a human hair, Captain gives it a light pink hue, and a wafer-thin aluminum coating reflects the sunlight. The successful unfolding of the solar sail was a decisive moment in the ground tests of the telescope. The unfolding in space was one of the most critical moments during the commissioning of James Webb. The 14 by 21 meter solar sail ensures that the temperature at the telescope is a constant minus 233 degrees Celsius. The telescope's 4 instruments are cooled even further with the onboard cooling systems. In order to guarantee accurate measurements, cooling the instruments is absolutely essential for infrared telescopes. Any heat source in the vicinity generates reception noise in the infrared and would thus distort the recorded image.
You want to observe in the infrared with this telescope, and each of us has experienced infrared light, namely when we feel uncomfortable on a warm, humid summer day. The reason for this is that the water molecules emit radiation, and we're in this radiation bed. But since we now want to observe water molecules in other planetary systems, we naturally don't want the telescope itself to emit radiation.
The James Webb Telescope is a complex machine. In addition to a central power unit, there are systems for position control, communication, and thermal regulation. There are also propulsion units and the associated fuel. It took 2 weeks before the telescope was ready for the next phase of commissioning, the alignment of the mirrors and the calibration of the instruments. Then, in the summer of 2022, the time had arrived. Just over 6 months after its launch, the James Webb Space Telescope delivered its first images. Since then, the telescope has continually sent amazing data back to Earth. From the very beginning, James Webb has astounded us with images of galaxies, gas and dust clouds, and star-forming regions in unprecedented detail. The first images also included a new version of the famous Pillars of Creation, a spectacular array of gas and dust making up the star-forming region of the Eagle Nebula. The combination of data from the 2 main instruments of the James Webb Telescope provides a new view of the region. The young stars shine in the near-infrared, while the data obtained in the mid-infrared with the gas and dust clouds capture the extent of their birthplace. A fascinating insight into the nursery of new star systems.
What beautiful, colorful pictures. But that should make us wonder, is this really what it would look like if we were looking through an optical telescope from Earth? Not at all. We would just see these white dots as stars. So what do astronomers do? Well, these are infrared images. They assign a different color to every single infrared wavelength. And that creates this beautiful colored image. In other words, if we could see infrared, only then would it look like this.
The James Webb Telescope is equipped with 4 scientific instruments, which are housed behind the primary mirror in the so-called Integrated Science Instrument Module. 2 of the instruments are cameras, one for the near-infrared range, the other for the mid-infrared range. In addition, there are 2 spectrometers that break down the captured light into its components, allowing molecules and atoms to be detected. MIRI, the instrument for the mid-infrared range, has a camera and a spectrograph. The instrument contains a filter wheel with optical elements to narrow down the range of wavelengths. These filters turn the camera into a scientific instrument with which researchers want to find out more about the building material that planets find in their birthplaces, the disks of gas and dust around young stars.
If you want to observe objects, then of course you don't want to observe them at just one wavelength, but at several. You may also want to insert optical elements, for example a chronograph, in order to cover central stars of the planetary systems and then be able to observe the planetary systems. Here in Heidelberg, we developed all the mechanisms for 2 of the instruments, NIRSpec, and MIRI. And this is particularly difficult because these mechanisms must work at very low temperatures. And I think anyone can try that out. They can simply cool down a bicycle to a very low temperature and then nothing will move. But we have to guarantee that this mechanism will move many times over a period of 20 years. And of course, without ever failing.
Not only the telescope, but also the individual instruments are masterpieces of engineering. The literally coolest of these is MIRI. It requires an operating temperature of just under -267 degrees Celsius. MIRI houses an imager and a spectrometer at the same time. This required an ingenious design to make do with the very limited space. The instrument uses separate light paths for the camera and the spectrograph. The instrument, which operates in the mid-infrared range, offers enormous potential for research into the formation of stars, the properties of dust and galaxies, and the exploration of alien planets. Time and again, the James Webb Space Telescope proves its enormous capabilities. Researchers observe young stars in their formation phase, as well as stars at the end of their lives and the remains of exploded stars, more precisely than ever before. Like the telescope, its instruments were also developed and built in international collaboration. In the case of MIRI, the Max Planck Institute for Astronomy in Heidelberg is one of the main contributors. The institute receives no money for this. The reward is observation time.
You build the instrument with a consortium, in our case a European-American consortium, and you receive time in exchange. We got a total of 1,000 hours back. That was the currency, so to speak, that astronomers are particularly interested in. So the way it works is that the currency you receive back is guaranteed observation time.
James Webb delivers in a quality that astronomers could only have hoped for. For the first time, they're observing very young galaxies at high redshift. Here, too, the particular interest lies in the areas where new stars are forming. So researchers are exploring the intense early phase of young stars and their interaction with their surroundings.
How do you actually recognize star formation regions? You do the following. First, you look at huge areas of dust clouds. And if you then look closely, you can see that these dust clouds have collapsed locally. These are the star formation areas. And if you then look even closer, you can see that these emerging stars, the so-called protostars, eject matter outwards via stellar jets. And this creates shock wave fronts at the ends, which can be seen very clearly in telescopes. If you look closely at the center, you can see that there is a rotating disk, the dust disk. And in it, you can see so-called planet-forming disks. These are dark rings. This is where the planets form, and they eat these rings free, so to speak. We now know that this happens everywhere in the universe, in our solar system too. Does this mean that our solar system is nothing out of the ordinary? Or is it in some way special? The answer is, our solar system is indeed special, because it depends on the details of planet formation.
With the James Webb Telescope, researchers can now also examine the so-called protoplanetary disks of young stars more closely. In this way, they hope to learn more about the mechanisms of planet formation, especially about the formation of Earth-like rocky planets. One such young star is Fomalhaut, around 25 light-years away from us. In its protoplanetary disk, scientists have identified an asteroid belt outside our solar system for the first time. With the keen eyes of James Webb, they are also searching for the building blocks of life. And they have found something. In Chameleon 1, a so-called dark cloud, they have detected water, carbon, nitrogen, oxygen, and sulfur using the James Webb data. The new super telescope is discovering exciting worlds for scientists. Its groundbreaking findings mark a new golden age of astronomy. With its far-reaching view of the universe, this next-generation telescope is transforming entire fields of research and creating new ones at the same time. The James Webb Space Telescope is the new workhorse of astronomy. It will answer many questions and generate even more new ones.
This is a gift to science, a gift to humanity, because questions can still be answered here that we haven't even conceived of yet. Questions we can't even formulate today, to which we will find answers through the James Webb Telescope. So it's really exciting and fascinating what can be done.
For the first time, the most intricate structures of neighboring galaxies can be made visible. These regions have been intensively researched in the optical and ultraviolet range with the Hubble Space Telescope. But the places where stars are formed were mostly hidden from Hubble's view. Thus, the crucial early phase of young stars remained mostly invisible. Their light does not penetrate clouds of gas and dust. The infrared instruments of the James Webb Telescope can see through these clouds and thus provide previously missing data on the birth of stars and the formation of galaxies, all the way back to the beginnings.
Wir sehen wirklich die ersten Galaxien.
We really are seeing the first galaxies. We're seeing the first quasars. The question is always, how typical are the objects for this time? It means we need to observe a few more objects. Sometimes a fluke of nature also helps us. If another galaxy lies in front of it and a gravitational lens amplifies the light, we can zoom in even further. So I think we're actually getting to the stage where we can see the first galaxies. And the first galaxies always mean, of course, that we see the first stars. And now you might be thinking, we can't focus in on the stars. That's true. But the stars produce the heavy elements hydrogen and helium, which means we can examine a spectrum and find ice and carbon there. Then we know immediately that stars are there and that the stars are forming or have formed.
The James Webb Space Telescope marks a new chapter in the exploration of the universe. With the ability to record even very weak thermal radiation, it provides scientific information and breathtaking images of objects that would never be seen with normal optical instruments. And the new astronomy machine can do even more. With its sensitive instruments, the telescope analyzes the atmospheres of foreign planets. By observing in infrared light, it detects chemical fingerprints that are otherwise unrecognizable. And so, the telescope plays an important role in the search for life outside our solar system.
Because the James Webb Telescope is so sensitive, it can do something that the Hubble telescope cannot. It can indirectly detect organic life on exoplanets. How does this work? When such a planet passes in front of the star and enters the starlight, this light shines through the planet's atmosphere, and then you can possibly see the absorption lines of ozone and methane. And these two molecules are so-called biomarkers. If you can see them, then you know that there must be plants on this exoplanet. So a very important part of its work will be to study the atmospheres of exoplanets.
It is one of humanity's big questions. Are we alone? Our Milky Way consists of over 100 billion planetary systems. Theoretically, researchers can find every star and every planet in our galaxy. With James Webb, they can now look at the atmospheres of extrasolar planets and search for clues, for signs of processes that show that life exists. James Webb is perhaps the instrument that will detect alien life for the first time. What this life might look like, or what stage of development it is at, is literally written in the stars. Nevertheless, researchers now have the right tool to find extraterrestrial life. And perhaps it is only a matter of time before we know that our own existence is no isolated coincidence.
What's really exciting is that we can now characterize the atmospheres of these exoplanets much more precisely using spectroscopy. We can do this for the ones we can image directly. We can record spectra. But we can also do it for those that have been discovered through these transit observations. On the one hand, we do this for giant planets like Jupiter, some of which are very hot because they're close to the stars. But we also do it for planets that are similar to Earth.
A rocky planet of the right size and at the right distance from a sun-like star. An Earth-like planet on which water is liquid. This is the object that researchers are looking for. No planet with these properties has yet been found. However, scientists are collecting more and more observation data, and they are investigating the physical and chemical conditions that led to the formation of the Earth, and thus to the emergence of life here, 4.5 billion years ago. Entire teams of scientists are searching for planetary systems that offer the fundamental preconditions for life and gain new insights in the process. Using data from the James Webb Telescope, an international research group from the Max Planck Institute for Astronomy has found water in the protoplanetary disk of the young star PDS 70, in the zone where Earth-like planets usually form. This discovery is spectacular. If rocky planets actually exist or form there, they would benefit directly from the existence of water there. The evidence points to a mechanism that could supply potentially life-friendly planets with water during their formation.
We all thought that Earth-like planets, because they're close to the star, are born dry, that there's no water there at all. But now we've found water reservoirs, and we've also found water reservoirs in other disks in this inner region. So these inner disks can have water, and we therefore have early access to water reservoirs for Earth-like planets. In other words, we have a star, an inner disk, two giant planets, and an outer disk. So these two giant planets have swept the region between the outer and inner disks clear. What we wanted to know now was, what is this inner disk made of? And we did this with James Webb and found that there's water in this inner disk, in the regions where Earth-like planets could also form.
The evidence provided by the data from the James Webb Space Telescope could possibly be proof that water is one of the earliest components of Earth-like planets. Water is essential for the formation and maintenance of life. Researchers have long debated how water came to our planet. Until now, the dominant opinion has been that asteroids could have brought this water to our planet from space. The proof that water can already be found in protoplanetary disks at least puts this theory to the test. The discovery shows that life-giving water can be present in areas of planetary formation, an indication that life could also develop in other planetary systems.
I don't think we're alone. I would say that we already know roughly the size of the universe, so it would be quite a bit of space for just one species. I think that would be a bit too wasteful with space. Now you might say that happens at home too. My wife and I also sometimes think, we live together in such a big house, and a lot of that space is somehow wasted. That's how I imagine it is with the universe. I really don't think all that space has been created only to put us in there.
With the James Webb Telescope, researchers are not only looking at the beginnings of our universe, but are also exploring the 4 gaseous planets in our solar system. However, the telescope cannot observe the 4 inner rocky planets due to its position in relation to the Sun. The images show Jupiter as we have never seen it before. Huge auroras can be seen in the north and south, and researchers have discovered a massive jet stream above the equator. You can see its veil-like ring system and the tiny moons Amalthea and Adrastea. Saturn, on the other hand, with its methane atmosphere, swallows up almost all sunlight and appears dark in James Webb's images. However, its rings of debris and ice reflect the light and shine brightly. Dione, Enceladus, and Tethys are also visible, 3 of its more than 140 known moons. Saturn's moon Titan is particularly exciting for researchers. James Webb's images show 2 huge cloud formations. Titan is Saturn's largest moon. It has a dense atmosphere and is the only known celestial object apart from Earth on whose surface liquids can remain. Rivers, lakes, and seas of hydrocarbons such as methane and ethane.
If we can now take pictures, then we can also take spectra of these objects. And I think the spectra are the really exciting part. The images show us how sharp our observations can be. And if we can do that, then we should always bear in mind that we can also record spectra.
Neptune appears light blue in optical light. The near-infrared images from James Webb show bright spots and stripes. These are methane ice clouds at high altitudes. The rings of Neptune, which were only discovered in the 1980s, are also clearly visible. In addition, the images also show some previously unobservable, fainter dust rings. The ice giant Uranus, the 3rd largest planet in our solar system, also shines in the focus of the infrared sensors. A total of 13 rings around Uranus are known to date. The James Webb Telescope has captured 11 of them in its images. Some of the 27 moons of Uranus can also be seen in the images. By observing the 4 gas giants in our solar system, researchers hope to expand their knowledge. And so James Webb's view extends from the beginnings of our universe to the present day of our solar system. It explores the universe, which is invisible in optical light, in greater detail and with greater clarity than ever before.
The James Webb Space Telescope, a tool for discovery that dwarfs everything that came before it. First, we can look back to the beginnings of our universe, with the oldest galaxies and their stars. Then there's the formation of galaxy structures, including the stars and their planets. And of course, this also enables us to better understand our solar system, and most importantly, to search for signs of life on exoplanets.
Humans have always been interested in exploring the starry sky. Where do we come from? And where are we going? These are fundamental questions. In their quest for answers, researchers are delving deeper and deeper into the universe, almost all the way back to the Big Bang. They seek to better understand our universe and its structure. They want to know how the first galaxies and stars were formed, and where and how planets form. And finally, how life was able to develop. Each new generation of telescope has changed our view of the cosmos. And with the James Webb Space Telescope, researchers now have a new and powerful instrument with which to rediscover the universe.